So hello everyone, good afternoon, and welcome to this ChEESE internal seminar. Arnau Folk asked me to apologize for not being able to join as he is in another meeting. And today we are pleased to have Filippo Mantovani as an established researcher at the Barcelona Supercomputing Center. He is responsible for the mobile and embedded based HPC group, and he graduated in mathematics and holds a PhD in computer science from the Università degli Studi di Ferrara. I'm practicing my Italian here. He's involved in the FPGA prototyping tasks of RISC-V-based accelerators within the European Processor Initiative, EPI, which is the theme of this presentation today. So Filippo, thank you for joining us, and the floor is yours.
Just 1 second, Filippo. I just have to say that this is being recorded for everyone to know. That probably it will be published, I guess, Tom.
Yes, I already talked to him. Yeah.
Just be aware.
Sure. Yeah. So thank you for the invitation and the nice introduction. So yeah, I'm going to talk about the EPI, but so there are two main ingredients, RISC-V and EPI. Okay, but the idea is to finish with a little bit of what we are doing in ChEESE, because part of the technology I'm going to present today is also involved in ChEESE. Okay, so let's start with the introduction of RISC-V. I would like to, if I would be in a room, I would say, raise your hand if you already know what RISC-V is. So try to use your button to tell me how many of the 9 connected people knows about RISC-V, please. Nobody knows? Good. Okay, so let me good, because I have a short introduction. So what is RISC-V? Maybe you are old enough to know the age in which for traveling you had to use this kind of cable, right? So you for every electronic device you basically needed the proprietary plug in order to connect to somewhere else. At some point somebody invented the other side of the cable, right? That is the USB, Universal Serial Bus. What is that? Basically is a standard that all the vendors at some point adopted. Okay, so nowadays almost everything is working with USB. Even Apple devices use USB, right? So why I'm starting from here? Because RISC-V is, say, the short definition of RISC-V is simple and modular instruction set that is proposed to be open and to be a standard in the world of the instruction set architecture. Okay, instruction set, I mean the set of rules that define the way in which software talks with the hardware. Okay, so here you have in this slide the details. It has been, say, started as a research project in 2010 in Berkeley, then ratified in 2014, and then started working on several extension and so on. When you in the slide, when you see the nerdy face here, is because you have something that you could study afterwards. So references, external references. Okay, so you can later study a little bit more. So as I said, RISC-V is a set of rules that you can use to code the instruction of your that basically comes from your programming language. Okay, so here in the right part of the slide you have the basics of the instruction set architecture of RISC-V. So really you can print it out in an A4. It's really compact. You have different fields in the instruction. You have type of instruction and so on. Okay, I'm not going to enter much in the details of this, but I want you to understand that is so a standard that the community is now pushing to have in the world of instruction set architecture. Good. So modular versus incremental instruction set architecture. Intel is an incremental instruction set architecture. Okay, so over time, look in this plot. Over time, the number of x86 instruction, x86 is the name of the instruction set of Intel, it has been increasing, right? Because every generation of new CPU has new features and maintains the old one, okay? So this has pros and cons. The big and very nice pros is that you can compile today so take a binary that has been generated in the 80s and probably run it in a CPU today, and it still work without any changes, right? The other side is that you are carrying on a lot of complexity. So this is probably a downside, right? So the idea of RISC-V is to be modular, so you can switch on and off extensions that has been ratified by the community of RISC-V, okay? That by the RISC-V International Committee. Now there are some of them are under, say, definition, some of them have been ratified, and they are basically added instruction that you can use to basically extend the functionality of your CPU. Okay, one example here is the V extension, that is the vector extension that has 186 instructions, a lot of them. This print screen is a little bit old now. Now we have already the 1.0, the ratified vector extension. So basically here the message is RISC-V is modular, so you can have a base set of instructions and then add extensions, okay, to have more functionalities. Now, of course, you can start thinking like, okay, but if I have a CPU and you add your extension, I add my extension, whichever ChEESE adds his extension for earth science, what we are going to end up into a jungle, right? And indeed, that's one of the possible risks. So to constrain this risk, the RISC-V ecosystem suggest extension, as I mentioned, profiles that are group of extension together, platforms that are basically the infrastructure around the CPU that allow some profiles to work, and modes that are basically way in which the user can use the CPU, right? In the analogy with the bicycle, extensions are features that you can put on your bicycle, right? Gears, lights, and so on. Profiles are types of bicycles, right? So you can buy a road bike and you know that a road bike will come with some extension that are agreed in the world of road biking, and mountain bike the other way. So these are profiles. Platforms are all the infrastructure that you need to be a cyclist, so bike lanes, traffic signals, and so on. While modes are basically the way in which you can approach a bicycle, right? So you can be a regular cyclist, you can be a mechanic, or you can be a builder of a bicycle, okay? So now take all of this and put it into the world of CPU manufacturer, okay? And you have different roles. Okay, good. So we defined the RISC-V, instruction set architecture. You know a little bit the ecosystem, okay? How it works. Now, the important message is it is supposed to be a standard. What we are pushing is a standard because we don't have a standard in processor architecture, okay? So if you see other area of the IT area, in the network, we have Ethernet and we have several implementation of it. What else? Maybe you are familiar with the web communication. We have HTTP and we have several implementations. So here in this table, you have the standard that has been defined and all the implementation, okay? For the processor architecture, in reality, this never happened. So there has never been a standard and different implementation. So RISC-V want to fill this gap. Okay, now moving out from the technical, going a little bit on the business model, RISC-V is an open ISA. So basically you can take it and build your own CPU. You cannot do it with ARM and Intel. The adoption is for free. you can still commercialize what you implement with RISC-V ISA. So if you do a CPU based on RISC-V, you can sell it. It's your CPU, you can sell it. What you cannot make revenue is on the instruction set itself, but on your CPU, you can do it. Everybody can develop commercial IP. It allows access to extension, and also it allows open source IP. So if you develop an IP, when I say IP, I mean your own RISC-V CPU. You can use it for example, I don't know, education or something like this, and leave it open. Okay, you are not forced to leave it open. You can leave it open. Okay. Good. So that's a little bit the business model. There is another legend in the if you start browsing about RISC-V, somebody tells you that is like Linux for software, but in the hardware field. That's not completely true, and the reason is because the software development, if you take the Linux kernel, you have the Linux developer, then you have to compile the kernel and use it. And the hardware is similar, right? You have the RISC-V IP developer, you compile it, you make a chip, and then you use it. So it looks like identical, but the real difference is this step, okay? Compiling the Linux kernel is almost free, while making a chip is millions of euros, okay? So there is a big difference here that needs to be taken into account. Okay, so take-home message now. RISC-V defines an open, free, and standard instruction set architecture. It defines a little bit a new business model, a new way of working. So we are not relying only on Intel building the architecture and selling the chip. And hopefully it's not dependent on market fluctuation, right? Because it's a standard, is pinned in the knowledge of humanity, and everybody can take it. So probably is less related to, sorry, is less dependent on war, bans, or something like this. If tomorrow somebody wake up on the other side of the ocean and decide not to sell GPUs anymore to Europe, we are out of luck, right? So there is all this geopolitical implication as well. So here you have a beautiful video of Kirsta Zanovic, that is actually the inventor of the RISC-V, one of the father of the RISC-V architecture that you can see. I was lucky enough to be in supercomputing watching live this. Very good. So now, one extension that is very important for EPI is RISC-V vector extension, okay? And here I just want to use an example to explain it because it's easier, right? So if I take the AXP with x86 intrinsics, I hope you're all familiar with coding. Otherwise, just don't fall asleep. Stay with me 5 minutes. We define two arrays of 32 elements, and then we define this AXP function that is doing this operation. Alpha multiplied by x plus y, and it stores the results in y, okay? So probably you are familiar with this. This is inside a loop. The loop is going from 0 to n minus 1. That is basically the number of elements of our array, okay? Good. If I want to vectorize it with x86 intrinsics, I should put these intrinsics here, okay? You should say broadcast the value of alpha, and then enter the loop and start looping over elements of, load the x elements on the vector x, load the y elements on the vector y, and then do the FMA operation and store it into the result, and then store the result back into the memory in the address of yi, okay? So these allow you to operate over a chunk of data that are the SIMD instruction of x86, okay? So basically you're not operating on one element of the vector, but you're operating on several of them. In this case, we are using AVF 512, we are using floats, so we are using 16 elements every time that we do the loop. Now this is nice. You see 16 is the number of elements. This is nice because n is 32, but what if n is not 32, okay? So if we have a generic n, you have to take into account the tails, okay? So you always have this a little bit dirty code that you have to handle by hand, the number of elements that are not multiple of the vector size. Okay, good. So in RISC-V, there is a little bit of, say, a more elegant concept, that is the concept of variable vector length. Basically, you have, let's look at the plot here. You have different vector. Each vector has a size that is called VLen. Each vector has a number of elements, that is the number of the vector length divided by the element width, selected element width, that is basically the size of each element. And so in this case, if the element is a double precision, so 64-bit, and the VLen is 256-bit, you can fit 4 elements in the maximum vector length. Okay. If the selected element width is 32, you can fit 8 elements. But then you can operate only on the green part. So you can operate only on a VL value that is lower than VL max. Okay, and that's a feature that allows you to have a variable vector length. Okay. This is something that allows you to avoid the tails that we were mentioning in the x86 example. And so the code of the x86, basically of the same function, the AXP function, would be like this. You load you broadcast the A value, the alpha value, then you enter the loop, and the first thing that you do, you ask the hardware which vector length can I use, and the hardware tells you the value of the vector length that you can use. And so you can loop based on the value that has been returned by the hardware, but also you know how many elements you miss, right? So basically this loop doesn't have the tails, because you operate the first iteration with, let's take the example here. If you have 10 elements in a vector and a vector length of 4, you can operate the first iteration with 4, the second iteration with 4, the third iteration you set granted vector length to 2, and you do just one iteration with a smaller vector length. Okay? And this is called vector length agnostic, so that means that the binary that encapsulate this kind of instruction can travel across different architecture, different chip that have different vector length. Okay, so take-home message, we focus on RISC-V vector extension that is called RVV, that supports variable vector length, and it is called vector length agnostic. Actually, RVV has a long set of other elegant features that can be found here. I don't have time now. It's probably really boring as well. So I leave here the pointer to the actual specification of RVV. And now I jump to the EPI project. I'm terribly late, but okay, let's try to have it in place. So EPI project, here you have the family picture with all the logos. Let's skip it. You can find it on the website. Let's jump to the technical. EPI wants to build 2 things, one CPU and one accelerator. The CPU is based on on ARM architecture, and is called REA, and the accelerator is based on RISC-V. We are talking about the RISC-V accelerator. We have the first incarnation of this accelerator that has been realized as a chip. It's called EPI, and is Global Foundry 22 nanometer, 27 square millimeter. It has been taped out in March 2023 and bring up in October 2023. So it's already 1 year old, basically. It includes 3 types of tiles, but we are going to focus only on the VEC tile. Let me explain. So basically, the STX tile is is developed by ETH Zurich and Fraunhofer, and is basically for machine learning, targeting stencil and tensor arithmetic. Then there is the variable precision tile that is developed by CEA for augmented arithmetics up to 256 bits. And then there is the VEC tile that uses the RVV extension that I mentioned before. Okay, Then there is the VEC tile is developed by Semidynamics, the core, BSc, the VPU, and the University of Zagreb, the floating point unit. Then we have the L2 cache and home node that is developed by Fort and Chalmers. Then we have a network on chip to communicate all these things together into the chip. That is the on-chip high-speed network, and also a link to the external, and that is developed by Extol. And then the physical design that is designed by Fraunhofer. And the board that is hosting this integrated by E4 and Seco. Okay, so here you have basically the technology. We are going to talk about, say, this part now, so the VEC tile together with the rest of the components that are basically making this as a standard CPU. What's special in VEC? Okay, there are two things that are special in this EPAC VEC. The first one is the Avispado RISC-V core that is developed by Semidynamics. The second one is the vector processing unit developed by BSc. So in the core, we have three basically special things. It can boot Linux. Being an accelerator is not trivial. So for example, a GPU cannot boot Linux. So this accelerator can. So you can use it as a self-hosted CPU actually. Then the Scalar in order RISC-V core releases several requests of cache line to the memory. Okay, so that's very important because it has the capability of sending several requests for feeding the VPU. And the third point is the core is connected to a vector processing unit through a standard open vector interface that is this block here. And here you can plug the vector unit, okay, that is what has been developed by BSc. Now the question is, which is the size of this vector that we are using? So we are using extremely large vector size, okay? So in Intel you can use 8 double precision elements in one vector. First I show you 16 floating point precision elements, okay? So that's equivalent. In ARM, you have SVE that can be up to 2048 bits, so 32 double precision elements. We are talking about 256 double precision elements, okay? You can see here the size of the vectors in scale. So that's really huge, okay? So there is this short vector, long vector approach. Let me skip it for the moment. So, but I guess in ChEESE, you are basically waiting me to tell you how to use this kind of hardware, right? So how do I program it? So EPAC VEC, what we promote for programming EPAC VEC is the auto-vectorization. So leave the auto-vectorization to the compiler, or you can put pragmas like Pragma OpenMP Cindy. So basically you guide a little bit the compiler to saying to the compiler where you know that the vectorization can happen. You can use built-ins, intrinsics, like in the example that I was showing before in the AXP. Not really suggested, but it's available both for C, C++, and Fortran. And also you can use assembler, okay? The arrow here is the arrow of the happiness, okay? So as long as you go down, you become more and more stressed probably, right? Because you probably want to stay up here. There is another philosophical line that goes here, that is everything that is below the Pragma OMP SIMD, it makes your code architecture specific, right? If you use built-ins or if you use an assembler, your code is not portable anymore. So you want to avoid that probably with a scientific application, because you want this application to travel around on different clusters. So how do I use EPAC VEC? Well, we promote this model of like a standard HPC system. You compile your code, we give you a compiler, you link your libraries, you write a job of Slurm, you submit your job, you wait the result, and then you study how well your code is vectorized. Okay, so here about EPI, take-home message. EPI is developing an ARM CPU and a RISC-V accelerator. We focus on RISC-V vector accelerator that is called EPAC VEC that can be self-hosted. It supports a variable vector length and it uses long vectors, okay? That's the point. Now, starting from here, I want to introduce the software development vehicles. That is basically the set of tools, hardware and software tools, that we provide to the software people while the hardware is becoming available, right? If you want to do a chip, is a work of several years, right? So you start with architecture definition, you do the RTL implementation, and so on. So during all this time, the software people are basically unable to use the new chip. So what we develop is this SDV, software development vehicle, that allow the people, the researcher, to use or to test the new architecture on a small scale before the actual hardware is ready, okay? So if you come today with your earth science code, we can give you an account, you log in, and starting from here, you can either test it on commercial RISC-V platform that are only Scalar, but this allow you to test your code if it is, say, RISC-V ready. Then you can emulate using QEMU plus some plugin that we developed, your code, your binary with vector instruction. And also we can give you access to some prototype based on FPGAs in which you can run your code, okay? So keep in mind blue, green, red, and now I go here. So imagine you come with your C or Fortran Scalar code, you compile it, you run it in the Scalar vector. So you have a Scalar binary and you can run it on the RISC-V commercial platform, okay? You can take the same code, enable the auto vectorization or put intrinsics, and you will get a RISC-V vector binary. And this you can either emulate it or run it on hardware platform that we provide to you. So you see that basically if you come with the same, with one source code, you get a binary with vector instruction, and then you can work on it, okay? And all this is built on top of standard tools, the LLVM compiler, QEMU, PAPI for reading hardware counters, and then we have also some instruction logic analyzer inside the chip. What can you discover? Well, this is the kind of study that we can do. So we can instrument region in your code that you are interested in. So you can see we color coded this region. Then we can divide in these regions what is Scalar, what is vector instruction. For the vector instruction, you can understand which type of vector instruction you have, how many of each type, and also you can understand, so we can provide you with the vector length that each vector instruction, you can match the color here. For example, this light blue is the vector load, VLE, and you have this vector length. 16,000 bits, that means 256 double precision elements. So in this case, all the vector instructions are using the maximum vector length. That is good. Usually it gives you a good performance. So basically these are the kind of study that we are doing on several real science application, okay? And you see here appearing the ChEESE logo, that is because we have this co-design work ongoing on the ChEESE Center of Excellence. Now, take-home message for the SDVs. The point is, while the chip are becoming available, we want the software people, the software developer, to be able to test the new architecture. So we developed this software development vehicle for being able to test this architecture. We can leverage SDV also to influence the hardware design, because if we provide feedback to the hardware designer in time before the chip is ready, they can modify slightly the hardware design. We can improve the compiler auto-vectorization or system software in general, libraries, for example, and we can study and improve vectorization of real scientific HPC codes. And here, if you allow me 2 more minutes, I have the example of vectorization of a ChEESE code that is, in this case, Minifold 3D. that I forgot to put it in the title. Sorry. And here I have the study that later I can give you the pointer for entering more details. So if I do a scalar vanilla trace, we have this structure. If I zoom in, if I enable the auto vectorization, you see that I have similar structure but less time. That's good. It seems that I'm going faster, right? So how much faster I'm going? Well, after a little bit of testing, well, you have, depending on the phase, on the zone of your code, but basically you have 1 point something gain, okay? It's very little. You expect to have more out of this vector architecture, or actually you want to know if it is good or bad, this speed up. So you can start looking into one time step that is composed by these 4 colors that we call phase. And then inside each color, you have different regions. And then if you start looking into the regions, you get this structure of colors, okay? And if you look into this, this is actually the output, a poster that we presented at the High Peak conference, okay? So if you start looking at the code corresponding to the various regions, sorry, you start discovering that there are non-vector friendly structure, for example, conditional inside loops that are breaking the auto vectorization, that can be easily rewrote in order so maintaining the code correct, so maintaining the correctness of the code, you can have a vector friendly version. And so basically studying these, I'm not going now in the details, okay, but studying all these phases at the level of source code, you can have a code that is more vector friendly, but still portable. And here you have the gain in this plot. Basically, if you look at the bars, is the execution time, okay, in cycles. So every column is a new version of the code that has a slight improvement. So you see that we are gaining a speed up of almost 7 in this case. But the same code is portable, so you can go to Mare Nostrum and you see that you have still some gaining as well. Of course, not big as in RISC-V, but so the message here is the effort in having your code vectorized for RISC-V and so on is also beneficial in other architecture, not only in RISC-V. Okay, if you maintain it as a portable because you don't use intrinsics. So here I have 2 more slides. One is reference that are related to ChEESE. This is a paper that has been already presented at PPAM last year. This is a poster that has been presented at the High Peak conference. Part of one piece of the poster is this one. And this is a paper that has been submitted to FGCS a couple of weeks ago. Okay, this is not actually available, not because I don't want it to be available, just because it's really fresh. So if you are interested, you can just contact me. I share the PDF. In a couple of weeks, we will have it online as well. Other references, if you are interested in the EPI infrastructure. So this is specific to ChEESE. This is general. So if you are interested in the generally on the EPI work and the SDV work on the emulator, this is paper on the emulator and so on. So here you have other references, and here you have other curiosity or pointer to other source of information about EPI and RISC-V. And I think I can stop and I listen to your questions, if you have any. And now is when I discovered that the audio was off.
No.
We were hearing everything. Any
Very
questions?
Don't be shy.
I would have a very general question, if I may. Sorry, I just realized my camera is not on, but well, this is also not working.
Don't worry about the camera.
No,
We can
Sorry,
hear
I have to do it without the camera.
you.
don't worry.
We can hear you.
So very general, I mean, you said that you're doing the OpenMP and then PragmaSimD approach for vectorization. So
Yeah.
you probably also do OpenMP for, so if does RISC-V then work as kind of an offload thing? So you do target offload?
Yes.
Okay. And the OMP kind of general parallelization approach with threads and so on. That would also work for another, but
Yes.
kind of at the moment you would do target, OMP target.
Yes. If I was mentioning at the beginning that this is a sort of different accelerator compared to the GPU, right? So what we are running now is native on the, so we log in on the CPU and we run the binary there. But we have also the capability of, for example, we can connect it, and we are doing it. We connect this chip to a, now we have it with Intel, so an Intel CPU, and you can put the Pragma offload and offloading a kernel, say, to the RISC-V accelerator and get the result. Actually, if you are at the URICH PC Summit next week, we have a demo that is using this technology. So if by chance you are there, please.
Oh, sorry.
Anyhow, yes.
Not be able to make
The
it.
short
No,
answer
but
is yes.
anyhow,
The offload is supported.
Okay. And maybe one second thing, if you talk about the vector instructions and long vector lengths, so you would still assume that the data fits into some innermost cache or some fast memory.
Yeah.
Okay. So that
there are caveats here, however, because you can imagine that since we have such large, let me go back to the size of this vector, right? Since we have such large vectors, so 16 kilobits, you kind of pollute a lot small caches, right? So L1, for example, we bypass it in the current design, right? Because basically, otherwise in a couple of load store of vector instruction, you basically are wiping out the whole L1. So the poor scalar core is always missing in cache. And so that's why we are skipping the L1 and going directly into L2.
Yeah, but if you think in stencil codes or something like that, you would have a couple of long loops probably, and they should be in cache then typically if you have kind of regular applications or just the normal applications.
Yeah.
Okay, thanks.
You're welcome.
Right.
I see the hand of Thomas.
Yeah,
Thomas. Maybe this is a trivial question, but I saw you mentioning LLVM compiler environment. May I ask how it looks for the Fortran side of it? What type of Fortran compiler can you offer on that platform, and what does it support?
Well,
what standards, for instance? Yeah.
We have so we are in sync with the main line of LLVM. So basically, whatever you have in LLVM now, we sync, I think, once every week. So basically, we are in line with the main branch of LLVM. We have Flang, and what I know, so I share the room with the compiler, the compiler guy, so I can ask him. But what I know, I know the side of the user, that we were able to compile Alia, for example, and other Fortran code here at BSc. That's basically the answer that I can provide. So we didn't just compile simple benchmark. We also used complex codes.
Okay, yeah, thanks.
You're welcome.
Yeah. Anybody else? I see nothing on the chat.
I have a question. If you want to try this,
if we want to try this on our own codes, can you provide access to a machine that with RISC-V?
Yes, actually, this, if I go back here, this is the easiest way to explain it. These two steps, step 1 and step 2, are completely available, and actually probably you already have an account because of our previous live or collaborations.
Okay, I'll try that.
No, I mean, jokes aside, these two steps are available. We have also a tutorial that is in a wiki that you can follow with a toy code that explains you the steps, but it's fairly easy. You enter, you module load the things you need, and then you start looking into that. This third step is sort of sensitive in the sense that here we have hardware that is under some agreement of projects. If you are part of ChEESE, for example, we should be your gateway, so we should talk and plan how to test the code. But in the short answer is definitely yes, you can access it. And the way to request access is just drop me a mail, I send you a form, you fill it, and is a lab infrastructure. So it's fairly easy.
Okay, thank you.
You're welcome. Piero.
You're muted.
You're muted, Piero.
Sorry, I would say, okay. So, if I understand correctly, you have not presented some result in terms of energy efficiency of this platform, or there is something, or so what is the characterization with respect to other platforms in terms of energy efficiency?
It's a little bit too early for delivering official data, in the sense that the chip we have is few cores, in this case 2 cores, and it is a technology. The 22 nanometer is a fairly old technology, so we do not expect to be extremely efficient, or at least efficient, comparable to the latest generation. There is also there is another things that complicate a little bit the measurement, that this chip doesn't have a memory controller on it, so we always have to use it connected to something else, so the measurement can be a little bit tricky. Okay, so still we have some measurement that is not public, so I can share it maybe offline, or at least comment it. The other comment that I can add is that we are working on the 2nd generation of this chip that is within the EU pilot project. Same technology, but new architecture, basically. And in there we will use 12 nanometers. So the technology is more like modern, still not state of the art, but is more relevant. There we will have a memory controller. So I would say that next year we will have a more accurate answer to your question. Still, if you are around, I probably can show a slide in which we have some.
Yeah, I hope so.
Sure.
So thanks. Yeah, thanks a lot. Yeah.
Anyone else? So I don't think so. Well, Filippo, I want to thank you again for your insightful participation and presentation. And I hope you all have enjoyed the seminar. And just a reminder that our next webinar will be on TAUP with Marta Garcia, also from BSc, on April 24. So thank you, and
thank you, everyone.
See you next time.
Thank you. Bye-bye.